Hello, my dear students. Let me start the new concept, that is rank of a linear transformation. This we had studied in UG, but here the presentation, the way of writing is different. The meaning remains same. If V is a finite dimensional vector space over a field F, then the rank of a linear transformation, that means the rank of T, is the dimension of what range of T. Range of T is denoted by the notation Vt. Okay, the dimension of range of a T, the dimension of range of T is called rank of T, and it is denoted by gamma of a linear transformation, that is T, that is gamma of T. Okay, with this definition, let me move to a standard lemma. If V is a finite dimensional, if V is a finite dimensional vector space over F, then for two elements, capital S and T, that means capital T belongs to A of V, then we have to verify the following conditions. Rank of ST is less than or equal to rank of a T. The second one, rank of TS is less than or equal to rank of S, and it is denoted by the notation gamma of ST is less than or equal to gamma T, and gamma of TS is less than or equal to gamma S. And the third condition is the gamma of ST is equal to gamma of TS. That means rank of ST is equal to rank of TS. This is equal to the minimum of what? The minimum of rank of a T and rank of S. In other words, gamma of ST, that means rank of ST is equal to rank of TS, and it is equal to rank of T. This is possible only when S is regular. Regular means invertible, that you know. Let me prove this lemma. S is a transformation from a finite dimensional vector space V to V. We know that, what we know? We know that Vs, that is range of S, is subset of what? Finite dimensional vector space, that is V. Okay. Let me operate T both sides. Vs of T is subset of Vt. Grouping. V of St is subset of Vt. Taking dimension both sides. Whenever the word dimension appear, that means we have the countability. Whenever we have the countability, that means counting. Either we have to take equal to, or less than or equal to, or greater than or equal to. Here it is less than or equal to. Dimension of V of St, that means range of St is less than or equal to dimension of range of T, that is Vt. And the notation we use here, gamma of St is less than or equal to gamma T. Similarly, we can prove for what? Yes, Vt is subset of V. Taking S both sides, Vt of S is subset of Vs, that is V of Ts is subset of Vs. Dimension of V of Ts is less than or equal to dimension of Vs, that is gamma of Ts is less than or equal to gamma S. That means dimension of Ts is less than or equal to dimension of S. Let me continue. If gamma of T, that means the dimension of T, that means rank of T is M, say, that means dimension of range space of T is M. That means we denote gamma T by what? Dimension of Vt, that is range space of T. Therefore, The range space of T, that is Vt, has a basis. Whenever we see the word dimension, that means it should be a basis of what? Basis of a vector space containing what? How many elements? M elements. Let me take a set containing M elements, say W1, W2 and so on, Wm. We have to verify that. What we have to verify? We have to verify Vt of S is spanned by a set containing the vectors W1s, W2s, Wms. Let me continue. For W belongs to Vt of S, we have W equal to XS. As you know, I want to convert belongs to equal. That means I should have elements on both sides. W belongs to Vt of S. I'll write it as W equal to XS, where X is an element of range space of T, that is Vt. So we write it as W belongs to Vt of S means W equal to X S, where S means what? Sum of what? Linear combination of vectors of W, that is gamma I, Wi. If you open this one, what you'll get? You'll get linear combination of vectors of W's. Operating yes both side, because what we have here, since W equal to XS, therefore W can be written as summation of lambda I Wi of S, grouping. So after grouping, we can say that Vt of S is spanned by the set containing the vectors W1 S2 Wm S. Therefore, dimension of Vt of S is less than or equal to M. That is dimension of grouping again. That is dimension of V of Ts is less than or equal to M only. Similarly, we can prove it for St also. Gamma of St is less than or equal to M. What M stands for? Rank of S. Hence, gamma of St is equal to what? The minimum of these two, that is rank of T or rank of S. Okay, let me continue. Since S is regular, that means if S is regular, 100% it is onto. If it is onto, then we write Vs is equal to V. Operating T both side, Vs of T is equal to Vt, grouping, taking dimension both side. This is equal to, that is dimension of V of St is equal to dimension of Vt. Dimension of V of St means rank of St is equal to rank of T. Conversely, if Vt has basis containing the vectors W1, W2 to Wm, then the regularity of S implies that since it is a basis, therefore the vectors are linearly independent and spans. We know the definition of the basis of a vector space. If it is a basis, clearly the vectors are linearly independent and spans. Since the vectors W1s to Wms span, let me recall, since it is a basis, therefore it is linearly independent and spans by definition of basis of a vector space. Therefore, it forms a basis. That means the V of Ts forms a basis. But Gamma of Ts. What is gamma of Ts? Gamma of Ts means, by definition, dimension of V of Ts. This is same as, right? This is equal to dimension of Vt. What it indicates? Gamma of Ts is equal to gamma T. That means rank of Ts is equal to rank T. Hence, rank Ts is equal to rank St, and this is equal to rank T. This is possible only when S is regular. This completes the proof of the theorem, the lemma. Let me take a corollary. If T belongs to A of V, if the element T belongs to A of V and S belongs to A of V is regular. Here, let me repeat. T is an element belongs to A of V. S is an element belongs to A of V, but it is regular. That means invertible. Then we have to show rank of T is equal to rank of St S inverse. This we have to prove. Since S belongs to the subalgebra, that is A of V is regular, by previous lemma, by the standard lemma, we write it as gamma of STS inverse. That means rank of STS inverse equal to, can be rewrite it as, we rewrite this one as gamma of what? STS inverse, grouping. Again, since ST is equal to TS because it is regular, again grouping, what we get? S dot S inverse means 1, therefore simply rank of T. Next lemma is also very simple and important also. If T S belongs to A of V, S is regular, then we have to show that T and STS inverse have same minimal polynomial. And you know the definition of minimal polynomial. Before I continue, before I take the proof, recall the definition of minimal polynomial. Let P of x be a minimal polynomial of an element T. What P of x? P of x is a polynomial of degree what? K. Since we have STS inverse, replace x by ST inverse, STS inverse. STS inverse can be rewritten as product of these two. Grouping, what we get? We get S dot T2 S inverse. In general, STS inverse to the power K can be written as S T to the power K S inverse. Therefore, the equation 1, this one can be rewrite as, we can rewrite 1 like this. P of ST S inverse. Here, since we have I naught is replaced by alpha naught is replaced by alpha naught I. Again, I is replaced by SIS inverse, and grouping we get this polynomial. Taking S common left hand side, S inverse common from right hand side. This can be rewritten as S dot P of T S inverse. And what that P of T stands for? P of T stands for alpha naught plus alpha 1 T2 alpha k T to the power K. If P of T equal to 0, then STS inverse equal to 0. Let me take another polynomial. Since P of T equal to 0, therefore P of STS inverse is also equal to 0. Let me take another polynomial. Q of x belongs to the set of polynomial rings that we denote it by f of x. And we know that degree of Q of x is less than degree of P of x. We have we have what? Q of STS inverse is equal to S dot Q of T S inverse. Since Q of T is not equal to 0, definitely Q of STS inverse is also not equal to 0, which is, that means if P of X is a minimal polynomial, then the equation 2, I mean this result 2 is also what? Then equation 2 is also satisfied. What it indicates? That indicates by definition both are what? Minimal, both have what? Same minimal polynomial. The minimal polynomials of T and STS inverse are what? Equal. That means same. This completes the proof of the lemma. Thank you.